How is everybody? Good? You've had great dates on the weekend or great homework groups on the weekend or great Netflix binges over the weekend. So, anyone have anything super exciting they want to share? Or boring, doesn't have to be exciting. No. Well, my weekend went pretty well until the very end when my son, he was leaving our house. He had two other BYU students. He was taking them home, and he put his phone on top of his car while he put some other stuff in the car, and then he drove away. And he didn't realize it until he got to campus and dropped them off. And so I spent an hour Sunday evening walking the streets and driving around trying to find a phone that may have come off. He has a Where's My Droid app, but it wouldn't connect. It probably broke. The phone probably broke. But anyway, nope. It is sad. So yeah, I've left things on the top of the car, and I've been in cars where I remember when I was probably 12. We were up in Provo, up here. We bought a bunch of groceries because I grew up in a small farming town. It was cheaper to buy groceries up here. You know, when you're up here, you may as well buy a bunch of groceries because it was much more expensive in town. And we left a gallon of milk on top of our car. So we drove like 5 or 6 blocks and stopped. No, someone stopped us, but we had driven 5 or 6 blocks, and it was still there. So, yeah, saved us. So, yeah. Hello. Does BYU have a football game this week? Who do we play? Is this the Louisiana Tech game? Who is this? Troy? And is it here or there? Here. Okay. Good. That's fantastic. The Wow. Sad. Well, BYU can do what the University of Texas did and charge people $50 to print out a life-size photo of you and stick it in the stands. You pay $50 to have your image right there. Yeah, I'm like, holy cow, someone's making money off that. Hey, tell you guys what, for only $20, I'll make a life-size photo of you and stick it in your chair. You don't have to show up, okay? Just, we'll set it up online, Venmo me. Has anyone been turning in their roommates for hanging out at parties where people aren't wearing masks? Raise your hand if you are this. Oh, were you there? No. Okay. It was called Young and Dumb? Yeah, it was called Young and Dumb. Wow. So anti-mask. Yeah, so, right. I don't think it's dumb. I think it's stupid and mean at this point. But. Wow, so sad. All right, let's just start. Take off our prayer for us.
Is Carson here?
Austin.
Professors and that they're willing to teach us, and please help us to be able to receive that teaching and do good in school. And we're grateful for all these blessings and more in the name of Jesus Christ. Amen.
Amen. Thank you. All right, start off. Let's talk about, I think my battery's about to die on my mic. We'll see if it lasts. Here's the homework. So watch the 3.1 pre-class video. So we're starting a new chapter. The chapter is on matrix algebra. You've been wondering what we've been doing so far. This is where we're going to represent matrices by just a big letter A or B and whatever. And we're going to start doing algebra much like you guys started to do algebra 5 or 6 years ago or however many years ago. With numbers, except this time we're doing matrices and numbers. So we've got real numbers and matrices in there. So watch that 3.1 pre-class video, read 3.1, do the 3.1 WebAssign homework, and then do the homework of the section we're finishing today, the written homework, 2.3b. Okay? So before we start, before I open it up for questions, I'm going to spend some time. We are going to go through a few things that connect linearly independent and linear independence and dependence and span to solutions of equations and solutions of systems. And then I'm going to open up, we'll take some time to answer some questions, and then the last half of the class, I have a presentation where that takes some of the ideas we've been talking about and talks about how they're used in real life. So as I've mentioned before, I think in this class, I have a goal to prepare you for the final exam, but I also have a goal to help prepare you to use linear algebra in real life contexts. So in the real world. So the second half of today is going to be about real world stuff. Some of you, I know most of you are in 215, so you're getting some experience doing some real world linear algebra on real data sets and real world problems. At least one of these that I'm bringing up, I think builds into a lab that you're going to be doing in 215. So, okay, maybe there's two that are close. But. All right, let's look at this system here. We have 3 equations, 3 variables. Okay, we can think about it as an x, y, and z that we're solving for. If these columns are linearly independent, so these first 3 columns, okay, the columns of the coefficient matrix, if they're linearly independent, what can you say about the solutions of this system? So take a minute and talk to your neighbor, okay? Talk about what would we know and why we would know that in that situation. Yeah, I don't know what it's from, but maybe it is a warning. All right, how's that? Can you still hear me? I had a spare set of batteries, so. Okay. All right, let's come back together. Okay. So someone that, you can volunteer your neighbor in this case. If you heard someone that you thought had some really nice to say, raise your hand and volunteer your neighbor. But also if you have some nice insight for us, you can go ahead and volunteer yourself. So someone that has an idea to share. Anyone? Anyone? Bueller? Bueller? Does it mean that there's only one? Why would you say only one solution? It has to, wait, what do you mean has to be 0, 0, 0?
Because A, B, and C are linearly independent, which means if it was in row echelon form, it would be 1, 0, 0, 0, 1, 0, 0, 1.
Okay, so if you redo, since we know these are linearly independent, we'll have, each one of these will be a pivot column. So we can row reduce it to this. And what might end up over here? It probably won't end up being 0, 0, 0. It only would if these were all 0, 0, 0 to begin with. If these are linearly independent. So these could be anything, any numbers. Yeah. But you're onto something, that there would be one unique solution. So and here they're linearly independent. We row reduce, and we're going to have this. So we know exactly what z has to equal, exactly what y has to equal, exactly what x has to equal. Okay. Maybe I shouldn't have called those x1, x2, x3. Maybe we should call them something else. Okay. All right, great. Other things? Yes? What spans all of our three? The three columns. Okay, these three columns, if I think of them as vectors in R3, okay, there are three because I have three coordinates. So I have three vectors in R3. If they're linearly independent, they span all of R3. I can get to any point in R3 by taking some combination of these things. And this is just some point in R3. So I know I can get there. Okay, nice. Very nice. And there's actually only one combination that I can use to get there, because I don't have any free variables. I'll reduce this, I have to, it tells me exactly what my x, y, and z have to be. So, yes?
At least one of the d's would have to not be 0, right?
At least one of the d's would have to not be 0.
You can't have all zeros. Or is that something else?
Yeah, that's connecting to the definition where, yeah, they're different things. So that's, by the definition says, if I had, I don't know what vectors, here, yeah. I don't want to get into that right now, but yeah, it says the coefficients of these, when I combine them, if I wanted to equal the 0 vector, those coefficients would have to all be 0. So, yeah. Yes? This vector? Yes. So that's what it means if there's a solution to any system we're talking about is, there's a solution means I can take so much of this vector, so much of this vector, so much of this vector, and add those together, and I would get this one. Okay? So, nice. Okay. Any other comments? If these three are linearly independent. Any other comments about what we know? Does the solution have to exist? If they're linearly independent, then in this situation, we know it has to exist. Because we're in a situation where we span the whole space. We've got three equations and three variables. These three will get me anywhere in R3. So I know a solution exists. If the columns are linearly independent. And I know the solution is unique. Okay, if that's all, if they're linearly independent. Okay, yes?
If you have, like, for example, two parallel lines, and then a third one that, like, angles out between them so they don't have an intersect, and then without an span three different dimensions.
So if you interpret each of these as an equation, and each of these is an equation of a plane, and if these are linearly independent, if the columns are linearly independent, then the rows are independent, and so you can't have parallel, you wouldn't have any two parallel planes. So yeah, we're going to come back to the geometry. I'm just going to do it in 2 dimensions. A little, it's easier to make sense of if I think about equations in 2 dimensions than 3. But yeah, those if you did have parallel planes, then then that means that two rows, you have at least two rows, yeah. The set of row vectors are dependent, and that also means the column vectors are dependent. So you can't have, yeah, if it's independent one way, it's independent the other way. So, yeah, it's crazy. So, well, no, I lied. For a 3 by 3 matrix, yes. Like if it's square, yes, but not necessarily if it's non-square. So. Okay, what if I said, hey, A, B, and C, these columns, they are linearly dependent. Okay. Then what can you say about the solutions to this system of equations? Okay, you can talk to your neighbor about that.
Yeah. Yeah, so I think it depends on the span, and then it depends on, so we're saying it kind of depends on what D1, D2, and D3 are, and whether or not that lies in the span of the matrix, right? So you
That's
can
right.
either have no solution, one solution, or, but I don't know if you can have infinite solutions when,
You actually can't have one solution.
oh, really? Okay.
Yeah, if there is a solution,
Okay,
you
you
have
can,
to
like,
have
change the-
you have to have multiple. Yeah, there will be infinite.
So there's either no or infinite. Okay, that makes
Because
sense.
you're going to have at least one free variable when you row reduce. Because you've only got 2 pivot columns, and so you're going to have one free variable at least.
Okay, so the way I'm
You could
thinking
have-
of it is, because if you have things that are independent, and they can be combined in any way.
Yeah. All right. Scott, do you want to talk about what you just told me?
So we figured out that you can either have no solutions or infinite solutions, because it all depends on what D1, D2, and D3 are.
Okay, stop right there. So he said they thought you can either have no solution or infinitely many solutions, and it depends on what D1, D2, and D3 are. Okay. I have to repeat this for people that are calling in.
Because it depends on if that vector lies within the span of like A, B, and C.
Okay. So if D1, D2, and D3, that's a vector, or you can think about it as a point. If that point is in the span of these vectors, then the solution exists. But this could not be in the span of all these, right? They're linearly dependent. So do I span all of our 3 now? No. So I span some subset. So it could be a plane. That would mean I'd have 2 pivot columns. It could be a line. All of these could be multiples of each other, and then I'm just on the same line. Or I could just be at a point if they were all the 0 vector. But you're more likely to have a plane over a line. So as long as this is in this span, a solution exists. Is it going to be unique? No. Why not? Because you'll have at least one free variable. So you could maybe get something like that, or something like this. Okay, so if we have 2 pivot columns, then we might get something like this. If you have 1 pivot column, then you get something like this. And in this case, as long as this is 0, a solution exists. But I have one free variable, so there's going to be infinitely many. Infinitely many solutions. And what if this isn't 0? So if this is 2, then no solution. Okay. If this was 0 and this wasn't 0, no solution still. You can't have 0 equals 2. So no solutions. Okay, there's a question over here.
Couldn't you also have a situation where there's exactly one solution if all of them are the zero vector?
Yeah, if all of them, well actually no, because if all of them are the 0 vector, then I can take whatever I want times this, plus whatever I want times this, plus whatever I want times this, and that would still be 0. Right, right. Oh, you mean if this is the 0 vector? If this is the 0 vector and these are also zeros? No, because then I can multiply this column by 10, and that's still a 0. I still get a 0 vector out. So I can have 10 of these plus 0 of these plus 0 of these, and I get 0. And I can have 100 of these plus 10,000 of these minus 3 of these, and I still get 0, 0. Yeah, so there's still infinitely many solutions. If I have the 0 vector, if I have a 0 column anywhere, then I can easily get infinitely many solutions because I can multiply that 0 vector times anything, and I can change the coefficient. Okay, nice thinking. Yes.
But if they're all the same vector, then right?
If they're all the same vector, then it would still be infinite solutions if this was in the span of these. So if they're all the same vector, what's the span? It's just a multiple of that vector, right? So it's only a line. It would be a line in R3. Okay? And if this was on that line, and let's say it took 3 A's to get me to this point. Well, if these were all the same, then I could take 2 A's and a B. Or I could take an A and a B and a C. Or I could take a negative 10 of these and a positive 13 of these. Does that make sense? So I can start changing the multiples. And they don't even have to be the same. If this is a multiple of this and this is a multiple of this, I can start playing the same game. But it's just a little trickier to find the coefficients. So, great. Good job bringing up these issues. So if it's linearly independent, does it exist? Does a solution exist? Maybe. But if it does exist, then it's infinite. Oops. Sorry, what was that? No, there would be no unique solution if these are independent. So there's no, if these are linearly dependent, then there's no way to get a unique solution, no matter what you put over here. There's no way to get a unique solution. So infinite, but yeah, we don't have to have a solution. We could end up in one of these situations. Okay, other questions? All right, what can you tell me about this system? I should say, what can you tell me about the columns of the coefficient matrix? There are 4 of them. Nice. Okay, we have 4 columns or 4 vectors. What we mean by this is 4 vectors in R3. Is this a linearly independent or dependent set?
It's going to be dependent.
Dependent. We can know just by the numbers. You're like, there's no numbers up there, Brother Corey. Those are all. There we go. We just know by the in the best case scenario. Okay, let's say A is independent of B. Okay, so I can span a plane, some plane in R3. And then suppose C is independent of those, so it's not in the plane. Then I can span all of R3. And that means that no matter where this is, I can already get there with combinations of these 3. So I know that these are a linearly dependent set. Okay. Could a solution exist here? A solution could exist. Does one have to exist? So it depends if it would exist if we knew that there's at least 3 independent columns. Then there has to be a solution. Yep.
So to check to see if they're dependent, can you just do the dot product between each one? So that would be what? A, B, B, C, C, A. So do 3 dot products, and if they're all equal to 0, does that mean they're all independent?
No.
No, that doesn't work.
So, well, if they were all 0, then actually, if they're all 0, then yes, you would know. But there are times when they're not 0, and they would still be independent.
Okay,
So
okay.
then you would know they're orthogonal. That's even stronger. But yeah, usually we have to row reduce. But sometimes there's ways. If you can quickly see one is a multiple of another, some other things, then you can just look. So if there's at least 3, if there are 3 linearly independent columns here, then you would know you would have 3 pivot columns. Then a solution would have to exist because you're still spanning R3, and there would be, you'd have infinite solutions because you're guaranteed at least one free variable. But if you just know you have 3 equations and 4 unknowns, does a solution exist? Yeah, you don't know for sure, because you could still well reduce this. Maybe you only have 2 independent columns. You could row reduce and maybe get something like this. So you've only got 2 pivot columns. And what do you have left? This could be 0. Great, you have a solution. Okay, infinitely many, because I've got 2 free variables. Okay. Okay. But what happens if this isn't 0? No solution. Okay. So then you got no solution. And you might only have 1. You might only have 1 column. You'd have zeros here, zeros there. So it might depend. But if you're row reduced and you had 3, once you start row reducing and you have 3 pivot columns, then you know a solution exists because you span the whole space. You're going to have infinitely many, but at least you know that one exists. You can keep them. Okay. Any questions about this?
So if there's 4, you know that it spans all of them.
You don't actually. Yeah. I said if you do know that you have 3 independent columns in here somewhere. Yeah. If you've got a set of 4 and you know at least 3 of those span, at least 3 of those are independent, then you know there's a solution. But if I just give you 4 vectors in 3 space, they still might all lie in the same line or just all lie in the same plane, and you don't know. In some ways, I think there's a better chance of one existing if you're kind of putting in random things. But, so. All right. Yes. Okay, let's do this example, because it's a nice one to work with the geometry on. Okay, and then hopefully I can answer that question. So don't let me start my presentation without coming back to your presentation. I'm without your question. Okay, here we have 2 columns, and like 2 column vectors, and another, a point in R3. What about this situation? Does a column? Right, does a solution have to exist in this situation? What if I said these are independent?
And you span a plane.
I span a plane, but it's in R3. So this point still isn't guaranteed to be in that plane. It's in R3. So even if they're independent, even if they're independent, I'm still not guaranteed in this situation. Yes? Right, yeah, in this situation, if they're not independent, then, yeah, these are all in the same line. They would span the line, or if they're both a zero vector, they're at a point, but that rarely happens, right? So, yeah, so if this is some combination, if this is some multiple of this one, then they're all in the same line. If these are independent, and there is a solution, what can I say about that solution? It's in the span. So if these are unique, I'm going to be able to row reduce it to this. If there is a solution, that will be 0. And it's unique. If there's a solution and these are independent, then it's a unique solution. So there's only one possible combination. I have to take so much of the A column, so much of the B column, add those together, and then I can get C. Geometrically, what I'm talking about is, this is hard to draw in 3 dimensions, but so here's like the X, Y, and Z axes. And I can think about these as two vectors in this plane. They're independent, right? 2 vectors in this space, and they would span some plane, that would stretch out in there. And if there's a point in this plane, then how many possible ways are there for me to get to that point with these vectors? There's only one way. They're independent. I'd have to go to just take so many of these and so many of those. Okay, so this is getting to your question about, what's your name in the back? Ryan, this is getting to Ryan's question about the geometry and infinite solutions. If you think about it this way, these are independent. These are the only 2 vectors I have to work with. I'm spanning a 2-dimensional plane. Then I only have this. I only have one option to get there. But if I have another vector in that plane, now I'm back to this situation. They're not all 3 of them are not linearly independent. Okay, and what does that have to do with free variables? That means I have a free variable because I can span 2 dimensions with my 3 vectors. So I have one free variable. Yep, they are. If they're independent, they all span the same plane or same line if you're down to 1. Yep. If these 3 were all on the same line, or we'll pick another 3. So then I can just change colors. Okay, if those are my 3, a solution could exist. It would just have to be on that line somewhere. And I could write that, I could get there in lots of different ways. I could shrink this one, I could shrink that one, I could shrink this one, and I could do multiples and combinations of those. And I would actually I'd have 2 free variables. I have two extra vectors on here that I don't need. Yes. Yeah, that's how many, you can think about it as how many redundant vectors you have. So, yep. You can also think about this situation in R2. And you can think about it as a system of equations. So this is 3 equations on the plane. So we can think about this as 2 vectors in R3, or 3 equations of lines in R2. So think about it both ways. And for a solution to exist, all 3 of these lines have to go through the same point. There has to be one point, one x coordinate and one y coordinate, that makes all of these true. Okay? But there's lots of different ways these could intersect. They could all be parallel. 2 of them could be parallel. They could just none of them be parallel and just not intersect at any one point. And all of these are no solutions. Yes?
So in this case, would we consider this system to be linearly independent or dependent? It looks like it's 2 vectors in R3, but it could also be considered
it's 3. Well, if I said these were independent, it's either a plane or a line or a point in R3. Like this spans those 3 things, right? If they're both 0, 0, you end up with a point, but you're not going to end up with that. So these either span a line if they're dependent, or they span a plane in R3. So,
What would those different solutions look like?
and those are the things we were talking about over here. So if they span a line, then for there to be a solution, this point has to be on that line. If it's not on that line, no solution. And when you row reduce, if you row reduce that situation, you're going to have something there, and then something else there, and then who knows down here, right? So if it's on here, you're going to have 0, 0. Okay, and you're going to be, that's what you'll end up with. But oh, I guess this is 3 and not 2, but I was thinking of these 2. Okay, I don't know, Albert. I don't know if I fully answered your question. So try it one more time.
Well, just because you mentioned a couple minutes ago that, these like if we consider them to be 2 vectors that are just represented vertically, then they could be linearly independent.
Yep.
They could be linearly independent vectors. But then you mentioned a couple minutes later that we could also think of it as 3 lines in R2 with X and Y coordinates, or that just in terms of X and Y. And so it looks to me like if it is 2 vectors like in R3, that they could be linearly independent, right? But if it's 3 lines in R2, then they're guaranteed to be linearly dependent because at least one of them depends on the other 2.
So don't think of, we haven't talked about a good way to think about lines in terms of, like vectors, sets of vectors are independent and dependent, but equations of lines, we haven't talked about like what that would mean for them to be dependent or independent.
Oh, okay.
So that's what we're doing. Yeah, because it's not a straightforward back and forth between this and this. So, okay, yes. Yes. No. Sometimes it's nice to be able to think about them both ways, and sometimes it's easier to think about them one way than the other way. So you can think about them as vectors in our whatever, or you can think about them as equations of lines in whatever many variables you have. So one, the dimension is how many variables, and the other dimension is how many coordinates. So, and when those are the same, you're dealing with a square matrix. We deal with these a lot, and so this is nice, especially if they're linearly independent. So we're very, very happy. It's kind of like the ideal. This is the ideal. If you have an n by n coefficient matrix and they're linearly independent, all the columns, we're happy. Things work out really nice. We have inverses exist and all sorts of other stuff, which we're getting there. Okay, let me. I mentioned before that I have 2 goals for this class. One is to prepare you for the final, and one is to prepare you for real world. I've already said that in this class. Boy, if you teach 2 classes back to back, it kind of gets to your head. Okay. So I'm going to go through one way to think about different ways to think about vectors. They kind of correspond to thinking about them as the rows or columns. And then four different situations where in real world we're thinking about how to get a set of vectors that we can easily make other vectors with, and questions that come up of, is this in the span of this vector, these vectors and such. Okay, like these big questions. What is one vector a combination of the other vectors? That's a big question that comes up in lots of different fields. What's the closest we can get to a vector given a set of other vectors? Sometimes we can't get it exact. So like here, sometimes the solutions don't exist, but if they don't exist, if an exact solution doesn't exist, can I get close? And if so, how do I get the closest possible with the combinations of the vectors that I have? Okay, we'll do examples of this. How do I build a nice independent set of vectors that's a good set that I can easily or quickly make other vectors with? Okay, or makes good approximations with to other things. Those are like big questions. Speaking of big questions, I'll make it big. All right. Sometimes it's weird to add vectors. So here's a bunch of quantities related to me. I have my height, my weight, my arms, my kids. And I have someone else. They're shorter, but more muscular. That's why they weigh more. Okay. And we add those together, and we end up with a person that's 145 inches tall, 395 pounds, 4 arms, 8 kids, 4 vehicles, and $10,000 in student debt. Okay. Does it make sense to add that way? No, or at least in some sense, if we add them together, you know, combined we do have 4 vehicles, and combined we do have 8 kids, but you don't end up with one person with all of those qualities. But this is exactly how we were adding food in the peanut butter book. You can combine foods and get a new food that has all of those qualities. But there's another way to handle this. So for this, I'm going to go to a real data set. This is the 1, 2, and 3. Those columns represent different individuals. Okay, and there's a bunch of medical information about them. Their percent body fat, their age, their weight, their height. And then the rest are measurements around body parts. Okay, so, and I think they're all centimeters. So around the neck, around the chest, around the abdomen, around the hip, etc. Okay, so it doesn't really make sense to add person 1 to person 2. Like let's add those vectors, and then the percent body fat is 19.5. I mean, it's like, it doesn't really make sense to do that. But there's another way of thinking about this. Instead of thinking about person vectors, we can think about body part vectors or an age vector. And this still might seem weird at first, right? Because what does a neck plus a chest mean? I'm like, it's kind of weird, right? So what I have done is I've transposed the matrix. You'll be reading about transposing matrices in a couple of days. So I took it from a 2x3 to a 3x2. Like you'll read about those. I transposed these, and now I can think about all of these body part vectors instead of thinking about people vectors. And it might seem weird at first, but if you think about it that way, you might be able to answer a really important question. So here's the real world question. Well, let me explain the real world problem. It's really hard to measure body fat. You need to have a special device that can weigh people while they're all underwater. And those things are expensive. They're not easy to do. Okay? It's not something you have just around your house. But it's very easy to measure your height, your weight, and distances around your body parts. If I have the distances around your body parts, can I predict what your body fat is? Or if I have, in this data set, I think I have about 150 people that range from young 20s to the 80s and all different sizes and shapes. If I have all of so if I have vectors, if I have all their information and this body fat vector, can I take combinations of those weight and height and neck and chest and whatever measurements and combine them to get the body fat vector? Maybe if that body fat vector is in the span of this 12-dimensional hyperplane, I think I have 12. How many do I have? I have age, weight. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I have 13 variables. Those are like my 13 columns, and I have 1, my body fat. That's like my augmented matrix vector over there. So if this if this body fat vector is in my 12-dimensional, it's a 12-dimensional hyperplane in 150-dimensional space. If I have 150 of those, 150 people in my study, chances are it's not going to be in that. Chances are body fat's not going to be in the span of all of these other ones. But if it's not, what I want to know is how close can I get? What's the closest I can get? Okay. Does the problem make sense? Okay. You've actually heard of this problem before. Does anyone know exactly what we're doing? This is called regression. This is exactly what you do when you regress, when you have one variable that you want to use as a predictor of other variables, or a lot of other variables, and you want to predict another one. You can think about it as lots of, well, we usually think about it as dots in 2 space, right? If you just have one input variable and one output variable, right? You've got these dots like this, and so you're trying to find the equation of that line. But it's actually easier to think about, the mathematics works out to try to find the equation of that line, or in our case, the equation of a hyperplane or whatever. Not to think about it as lots of points in 2-dimensional space, but in this case, 2 dimensions in a high dimensional, 2 vectors in a high dimensional space. So, and this is exactly the math, the linear algebra is exactly the math that statisticians use to find formulas on how to answer these questions. So that's exactly the math that, I didn't do this by hand, this is the software did, to come up with that equation right there. It turns out that some measurements aren't important. They're not statistically significant in predicting your body fat, but these are the ones that work. So there's your formula. And hold on, you can see the combination, right? I need 0.6 of my age minus 0.08 of my weight minus 0.44 of my neck plus 0.89 of my, like I'm combining these things, and that constant is actually just a vector where that's like the whole thing. It doesn't change, like age changes for each person. That constant of a negative 14.94, that's just a constant vector. That's the same value for all those. So there's our combinations. Yes?
Just curious, like how long would it take for you to actually do that by, like, do vector that big?
By hand? So not as long as you think, well, I don't know as you think. Give us like 3 or 4 more days, and we'll have the tools to derive a formula where we just have something we can just straightforward start calculating. That's still a huge matrix. That's going to take us a long time to do, because we're starting with a 13 by 150 matrix, and it turns out you need to multiply that by its transpose. It's going to take you a long time. But yeah, it's kind of crazy. But that's right. But that's exactly what people like Porter learn how to do, is to get computers to solve problems like that. But the formulas that we'll derive are going to be exactly what he's getting the computer to do. So, okay. A lot of times, there's lots of situations where you're not trying to get as accurate as possible. You're just trying to get close enough. Or yeah, just you have a good standard. You're like, I just have to get close enough. And the close enough is good enough because it allows you to be faster or use less storage on the computer. So here's screen imaging is a situation where they just have to get close enough. It's a situation where they only have 3 values: a red value, a green value, and a blue value. And each pixel that you see on the screen is just a combination. It's actually a combination of red light, green light, and blue light. And every little pixel has a value that has a value associated with it to make that light. It spans, those combinations span the visible spectrum for us. So you can get any light, any image, any color that we can see, we can get by a combination of those, or pretty close. They might have some technical physical barriers, but yeah, they span that set theoretically. Interestingly, yellow is a combination of green and red, but you only have red, green, and blue cones in your eyes. You only pick up those the lights of those levels, and then your brain combines them to interpret them as different colors. So that's you use red, green, and blue. You don't use yellow, cyan, and magenta to do it, because the computer scientists, they just have to get your brain, your brain to think it, and they're going to use the colors of the cones in your eyes. You already have. Okay. And so those are a minimal spanning set. Red, green, and blue are a minimal spanning set. They span the whole thing, and there's no redundant information. That's really nice. We're going to call that a basis later on. Okay. Went the wrong way. So compressing yes? Yes, it's a combination of red and green, and they have red and green coming out, and your eye interprets it as yellow. So if you want to compress digital images, then well, if you want to store digital images, then one way to store it is you can say here's the location of this pixel, and this is how much red, this is how much green, this is how much blue do you want. It turns out that's really it turns out that takes a lot of information to store images that way. That's called a bitmap. There's a lot more to a bitmap than just that, but that's the basic idea. So images are stored digitally. They are in these pixels, these squares. You can see I zoomed in. You can see in that upper left that they're just in a grayscale with these boxes, some scale from white all the way to black. And you could make this if you had vectors. You could talk about each square and like I said, say this is how much gray it has in it. But someone's thought, well, you don't have to talk about each square. You could talk about a square of squares, and then you could come up with this kind of basis. These vectors can make up any 3x3 square. They're black, but what you do is like 100% they're black, at 0 they're white, and you can scale you add whatever percentage you need to get things like the one up in the upper left. And but this is not a good basis. These are not a good set of vectors to build 9x9 things because, or sorry, 3x3 things, because if you leave any one out, you end up with a hole in your picture, and it's easy to notice the difference. But this is a really nice set to build images off of. This is what JPEG does. They don't do 3x3. They don't chop it up into 3x3 pixels. It's 8x8, and they have all of these sets. There's 64 sets here. If you give me any JPEG image, black and white if you give me any digital image that's black and white, I can reproduce exactly that image, a piece of that image, that's 8x8 image, with some combination of these. Okay, yeah. But why is this better? Well, it's better because naturally things have certain patterns, and if you have a dark cell, usually you have dark cells around it. Okay, if you have a light cell, you usually have light cells around it. And things like these lower right-hand ones, these checkerboard ones down here, they rarely come up in an actual photograph. And if you leave them out, if they do come up, if you leave them out, your eye doesn't notice much of a difference. So these things over here, you can leave out. I don't know exactly how much they leave out, but you can leave out those, and they rarely come up, and your eye doesn't notice much of a difference when you leave them out. So you're able to represent almost things that would take 64 pieces of information with about half that, or a little more than half that, and you get almost 100% of the information. So, and there's a similar thing. We're out of time, but there's a similar thing with sounds. When you record your phone, it takes 8,000 pieces of information every second to record your audio. But that's a lot of information to pass over. You know, if you're It's a lot of information for the cell phone to carry over to the next cell phone. So either you want to pass all that information or a lot of that information with a lot less information. And what they do, that's me saying hello, that upper one up there. You want to get, what they do is they use sine waves as the vectors. You can make any sound with combinations of sine waves of different frequencies. And so it turns out all your cell phone needs, this is the basis of MPEG compression and other things, is you actually don't need to know every single value for that 8,000 bits every second. You just have to know 200 or 300 values for what sign combinations you're going to put in. And that'll get you a second of information. I hope we can actually do a lab in this class, with this sometime. All right, have a great day. Sarah went over. Look for vectors, they're all around you.